In this lecture, we're going to talk about redox reactions. So redox, oxidation-reduction reactions, or redox reactions, are reactions when electrons are transferred from one substance to another. So oxidation is the loss of electrons, and we say if something is oxidized, we call it the reducing agent, and reduction is the gain of electrons. So if something is reduced, we call it the oxidizing agent. And one acronym you can use to help you remember that is OIL-RIG. Oxidation is loss, reduction is gain. So, and these types of reactions were really just following the transfer of electrons, the movement of electrons. Combustion reactions are a type of redox reactions, and they're characterized by the reaction of a substance with oxygen to form one or more oxygen-containing compounds, often including water. And usually for combustion reactions, the products are either carbon dioxide and water or carbon monoxide and water. So this first example is methane reacting with oxygen forms carbon dioxide and water. The second example is ethane, which is the fuel we use in our gas, reacting with oxygen form carbon dioxide and water. So these are just a subtype of redox reactions. So when you look at a redox reaction, because we do care about the transfer of electrons, where the electrons go, the first thing we need to do is we need to look at oxidation states of the elements within the reactions. So there's some rules for that. And the first thing we'll talk about are non-metal oxidation states. So for example, fluorine, its oxidation state's always -1. For hydrogen, its oxidation state is always +1. For oxygen, it's always -2. Group 7A is always -1. Group 6A is -2. And group 5A are -3. So these are important to know because these oxidation states don't change for these elements within compounds. So if fluorine is bonded to something, its oxidation state is always going to be -1. If hydrogen is bonded to something, its oxidation state is always going to be +1, so on and so forth. And for the most part, these do correlate with their group numbers, what we see for their charges. But the thing to note is it's important not to confuse ionic charge with oxidation state, because something doesn't have to be an ionic compound or have a charge to have an oxidation state, so they're not quite the same thing. But you should learn this, but it's pretty straightforward. Here are the rules for assigning oxidation states. So the first rule is the oxidation state of an atom in a free element is 0. So for example, copper metal, just by itself, no charge, its oxidation state is 0. Chlorine gas, Cl2, its oxidation state is 0. So basically, if you see any element by itself without a charge, it's going to be 0. And then you just have to remember the diatomics. So if you see H2, O2, Cl2, so on and so forth, they have an oxidation state of 0. The second rule is that the oxidation state of a monatomic ion is equal to its charge. So for example, calcium 2+ has an oxidation state of +2. Chlorine ion has an oxidation state of -1. So the subtle difference between here and here are atoms by themselves without a charge. Here are atoms by themselves with a charge. The third rule is the sum of the oxidation states of all atoms in a neutral molecular formula is equal to 0. So for example, here in water, we learned on the previous slide the oxidation state of oxygen is 2. The oxidation state of hydrogen is +1. So -2 and +1. So 2 times the hydrogen oxidation state must equal 1 times the oxygen oxidation state. Or those added together must equal 0, which is the case. Again, oxygen has an oxidation state of -2. Hydrogen has an oxidation state of +1, so 2 times +1 plus -2 is 0. But if you have an ion, the oxidation states must equal the charge of the ion. So here, 1 times oxidation state of nitrogen plus 3 times the oxidation state of oxygen must equal -1. We know the oxidation state of oxygen is -2. So we can use that to figure out what the oxidation state of nitrogen is in this compound. The next rule is that in their compounds, group 1 metals have an oxidation state of +1. So sodium and sodium chloride has an oxidation state of +1. The second rule is group 2 metals have an oxidation state of +2. So calcium fluoride, the calcium in this ionic compound, has an oxidation state of +2. And then finally, in their compounds, we assign nonmetal oxidation states according to the hierarchical table shown in the previous slide. Entries at the top of the table have priorities over entries at the bottom. So we're talking about this. So for example, this is the hierarchy. So fluorine, you'll always assign fluorine first as -1. Hydrogen, you'll always assign it first as +1. Oxygen, you'll always assign it first as -2, so on and so forth. So if we're looking here at NO3, well, generally nitrogen is a -3 oxidation state because it's group 5A, but oxygen takes priority. So we assign oxygen first and then use that to calculate the nitrogen. So these are, the higher up the rule, the more important it is. So you always go with the rule higher up in this list, and that will take priority. So really for this, you just need to do a lot of practice problems, but it's pretty, once you get the hang of it, it's pretty straightforward. So let's look at this. So here we have carbon plus sulfur to make carbon disulfide. Carbon here is just by itself, so according to the rules in the previous slide, its oxidation state is 0. Sulfur here by itself, so its oxidation state is 0. Over here, we assign sulfur before we assign carbon based on these rules. Sulfur is above carbon. So we know sulfur is -2. The sum of these oxidation states must equal 0. Since I have 2 sulfurs, I have 2 -2 charges. So carbon's oxidation state must be +4. 4 plus 2 times -2 is 0. So then we look at what changed. So for carbon, we went from 0 to +4 oxidation state. So we lost electrons. And remember, oxidation is the loss of electrons. So carbon was oxidized. Sulfur went from 0 to -2, and so it gained electrons, so it was reduced. So that's kind of how you do it. Let's get another example. So here we have calcium. Calcium just by itself is 0. Here we assign hydrogen first. So hydrogen is +1. We have 2 of those, so oxygen must be -2, so the charges cancel. We go over here, we first assign hydrogen. Again, we have to go in the hierarchy for the rules. So hydrogen is +1. Then we assign oxygen. Oxygen's -2. And so calcium has to be +2 in order to do the charge balance. And calcium, since it's a group 2 metal, it's always going to be +2. And then we look at hydrogen gas over here. Well, it's just an atom, or just an element by itself, so it's 0. So we look at the movement of electrons. So oxygen over here started with an oxidation number of -2, ended with an oxidation number of -2. So it did not change. Nothing happened to that. Calcium went from 0 to +2. It lost electrons, so it was oxidized. Hydrogen went from +1 to 0. So it gained electrons, so it was reduced. So that's kind of how you do redox reactions. Again, I would just do lots of practice problems. Once you get the hang of it, though, it's pretty straightforward. On D2L, I put up a redox practice sheet and its answers, so I would also do that.